Cool.
Okay. Yeah, you can begin whenever you're ready.
I think I just make sure that I see what I'm talking about. So, one second. There. Okay. Cool. Well, that was not what I was intended. That's better. Almost. It's starting. So, hey, my name is Benedict. So I'm from Germany, and I was a bit as well, not surprised, but it was a bit spontaneous to decide to give some kind of lecture today. So Manu is in London, so I was supposed to meet Manu, but it's like we went apart from each other. But anyway, I talked to him on Saturday, so he briefly mentioned what would be interesting to you. So today I wanted to give you a brief introduction into optics again. And so what we're doing is modular optics, and to my surprise and to your surprise as well, I have even something in my backpack. So because I was in Woodsall, that's near Boston, and I gave a lecture for biologists in marine biology, and they, of course, use microscopes with it, but they don't really know how to build them, and that's kind of what we're trying to do or to solve. Like, because microscopes, they are sometimes very complex, but for me they're not. And so what we kind of build is the Lego for optics in a way, and it's all open source. And what I would like to teach today, or maybe also start the discussion, is a bit like how can you start with that, and like maybe also taking away a bit the fear of like building something like high precise optics. But first of all, I mean, you probably are into open source already, so you have probably heard what's open source and stuff, so I don't need to go too much into these details, but this is definitely the driving force for me, because I've done through this whole process of becoming a PhD at one point, and I think even during my bachelor thesis, I've read this sentence, like, this data is available upon reasonable request. That's like, you're doing your stuff. By the time I was building little holographical tweezers, and then I built everything, and then I needed the code in order to kind of generate the holograms, and then was kind of behind not even a paywall. It was just not there, and the person who wrote it, he also was not really willing to share it, and then the whole thing was a bit useless. So it's like source, you start from somebody's work already, so you don't start from scratch all the time, which is super cool, I think, not only in academia but also in industry, because this is something, I think I told you the story already briefly. So it's a bit of a private story, but my neighbor seems like he's also in academia. He's also a research group leader doing something with DNA, kind of sequencing, fish labeling and stuff. Anyway, so he had a microscope which he needed for a project. It's basically microscope, but it's now basically a 500,000 euro piece of scrap heap, because the software that was running this device was broken during a flashing, like an upgrade process, and then the company went bankrupt, and now it's literally all the components are perfectly fine. It's just you cannot operate it anymore. And imagine something was open, you could just use it, you can manipulate that, and we still have high hope that we can use it, like we can make it alive again with open source tools like Micromanager and all these things. So it's just for you to consider, hey, open source has many nice aspects. Yeah, tools that you use, probably, I think I don't need to go over these, but yeah, open source is like an envelope, and that was something my research group was doing. So open instrumentation was something I was doing. Now, since I'm more part of this whole company, Open UC2, I'm still doing the same thing, but not in the research context anymore. And so the cool thing, well, we can do all these things now. If I'm looking around, we don't need to talk about this so much anymore, but we have all these tools available now, especially like 3D printers. When I'm looking on to your right-hand side, there's a Stratasys, which I think was dominating the market until like 2011-ish. And then one of the big patents was lifted, and then people started building their own little rep machines. And now I think everybody has printers. I mean, only in this room, I see like maybe 5 of them. Some proprietary, but like most of them are nowadays open source. Stay based on open source technology, and this is something, I think, really pushing this field forward quite a lot, and also optics. Yeah.
What is the video you showed on
Top right this year?
Yeah.
Oh, this is an injection molding machine.
Ah.
So we have a little desktop injection molding machine where you can print the molds and then do like very small batch injection molding stuff, which is kind of fun. It's an art of itself. I have absolutely no clue how it works, but it's cool. Yeah, and then of course there's a recycling to like put the stuff that you do back in the cycle, printing PCBs, ordering PCBs on demand, CNC machining, all these kind of things are tools that we use now, which we didn't have access to, like say 10 years ago, at least not for the budget. Cool. So that was the starting point where I think Frugal Optics was kind of born. So that was the beginning when I was doing my PhD. It's like 2018 is already quite far ago, or 19. So what we basically did was we literally just replaced this 20,000 euro camera with a 20 euro module from a I still have my cell phone. It's a monochrome camera, so you capture a little bit more light because you don't have the biopattern. Because like the way cameras anticipate colors is like you have 3 color channels and they are kind of blocking away certain amounts of light. But here we were able to capture all that light and then went from the typical fluorescent image, what you see maybe on the right-hand side, to a super resolved image. So it's a bit of photochemistry. So it's not like all molecules illuminate at the same time, but they kind of blink and then you take a video and then kind of you have localization instead of resolution, but in the end, it's a resolution which is then going down to 18 nanometer, which I think is pretty cool. And so I think this was the moment where I said like, okay, we don't need to have like a 200,000 euro equipment to get the same results eventually. So, and then this whole journey started. And on the way, I mean, I think there's something maybe Manu already highlighted. One can think out of the box. Like if you open old equipment, like say, for example, this 1,000 euro machine, you will find lots of cool things. But you can also go down to say, you could just go to, I don't know, what's the local shops here, like the thrift stores. You go to the electronics section, then you may find an old DVD player. Maybe some of you still know what that is, but there's very cool optics involved there because the way it works, you probably know, it's a disc that's rotating. You have little information embossed in the silver film, and you have to read it out somehow. And what it is, it's basically a confocal microscope because you focus on this thing here and you read out well, they are actually diffraction limited, let's say. So you're working at the physical possible limit to like squeeze as many information on the disk as possible. That means while it's rotating, it's wobbly because it's not perfectly flat. You have to maintain the focus. You have to maintain perfect focus quality. And so there's a whole bunch of different electronics inside this module. It's kind of a microscope, but it's also an autofocusing mechanism and different laser channels. You have Blu-ray that works in the blue, then you have CD that's red, and then you have, sorry, CD is actually infrared, and then DVD is red. And this is all packaged in a device that is like this size. And wouldn't it be cool to benefit from these kind of already well-engineered mass-scaled items, for example, for a microscope? And this is something where we also did once in a while, like you see then like the optical diagram here. And the way it works here is like you have this one DVD, sorry, the one lens that is facing the DMD, the beam splitters, and then the detector and the laser diode. And the detector itself can also sense the distance between this lens and the DVD in order to focus it such that you minimize the focus spot. And the way it's done is using a quadrant diode. And quadrant diode is basically a very, very simple camera with just 4 pixels. Then you do a very simple mathematical formulation. To measure in the end, since you have one element that has some kind of astigmatism. Astigmatism is, I think some people have that in their vision. Basically, if your lens is not perfectly like symmetrical circularly, but rather like I don't know, like a rod-shaped lens, more or less. And then you induce this focus along the Z that is not symmetric, and then you perfectly know along the optical axis where your values, which I think is pretty nice. And so, I mean, you could use that already as an autofocusing element for your microscope, which we have brutally done here. So basically just placing a little objective lens on top of this thing here. We read out information, and what you see here on the oscilloscope is basically the focus value. So like if it goes up, then we're going up in the focus, and down, then it's going down. So and this thing literally costs like €5 if you get that from eBay. It's mass scaled, pretty cool. Or you can use this as a source of inspiration for your own device. So you just take the optical diagrams and then simulate that maybe, or just note it down. That's something we have done. So it's basically the same idea. You have a laser here. In that case, it's fiber coupled, it's infrared. There's a beam splitter. There's a, well, mirror here in that case, and then cylindrical lens here. You have the cylindrical lens and the camera, and then you, it's basically this cross. Like you have one focus position, you're going small, and then you have the other focusing position. It's not a perfect video here because it's just something I acquired a few hours before I flew back. But I think there is a lot of potential to just take something that's already well engineered. Maybe that's Frugal, either take it directly or maybe just know or like derive the information from either a patent or like just open the box and look what's inside and then apply that to your system. And I think over the years I've done that quite a lot. And I think I'm not quite happy with this graph yet, but there's this thing where you can really save a lot of money. I mean, imagine a €5 device that can do autofocusing where you buy that from Zeiss for €10,000. So you literally could save $9,995. But if I do that in a context of the research, and let's say I spend 2 months of writing code and designing the PCB, then like I'm worth €10,000 just in salary. So then like this advantage doesn't really pay off anymore. I mean, once people use it, then of course, then open source is nice. But like there's this balance between, okay, is it really cheap? Or do I need to spend actually quite a lot of time to get it running? And then it's actually not so cheap anymore. So then I think there's kind of a sweet spot somewhere in between, which I haven't really figured out how to call it. But this is something before you start opening a box, thinking about actually taking the parts for your project. Should I consider buying that eventually? Because I have the tendency to do that because out of curiosity, but there's also this thing, if you can buy it, rather buy it. Okay. That's the thing about availability. And what we have tried over the years with optics in general, like for example, here there's a microscope per meter. You know, who knows what's a microscope per meter? And I'll teach you that later. So this is typically very expensive. This is mostly 3D printed. At least in Germany, this is part of the curricula. So everybody should learn that, like do that with their hands once in high school, for example. But since teachers don't have printers or cannot buy these parts, because if you typically buy these, say like, I don't know, €10,000, like one kit from Thorlabs, for example, there was a bit of our mission to make these optics somewhat more available, accessible, and approachable. And this is also what this whole thing is driving this open UC2. Because in optics is relatively difficult. Like in electronics, nowadays, I mean, you have shelves of parts I see here, resistors, like Arduinos and stuff. But with optics, it's difficult because parts are not available. The knowledge is quite scarce, and it's also a bit of a black box. You don't face optics so often, even though optics pretty much everywhere, like the projector, like the way we're communicating here is all optics. Yeah, and so going down, so I'm more this Arduino, you probably know, it's to me at least has revolutionized the electronics part, because literally I was doing this thing, soldering electronics, developing them. It took time, it never really worked. And then Arduino has tons of code. You can do whatever, electronics, like robotics, home automation, use it for all kinds of stuff. And so to me, together with Raspberry Pi and all these things, it really revolutionized electronics development. And so in optics, you can observe the same, since you have, for example, a microscope, but can also be, for example, the magnetic interferometer. You have hopefully, well, in many cases, light sources, lenses, samples, or objective lenses or cameras. And basically what you do is like you just concatenate them somehow to form a system. And since optics follow this physical principle called Fourier optics, which I don't want to go too much into the details here, you can modularize that. And that's, to your surprise, it's a cube, and that makes things very simple to assemble. So with these cubes, then we created like a library, like you would do that from Arduino sensors, where you have I2C sensors or all kinds of actuators that can be plugged together and be operated together. And it's the same for the cube. So we have an online library of printable parts, or like also you can buy them. And then you have a laser, camera, whatsoever to build something. And since I should also be a bit of a curious, actually, so I'm assuming whose background is somewhat optics. 1, 2, 3. Okay. So maybe for you or maybe for all of you. So what is your favorite device that you could never afford, but always wanted to have and could be, for example, replicated with the cubes? Because this is maybe where's a challenge later today, like thinking, how can we go from this into a producible setup?
I don't know if it could be done with the cubes, but electron microscope when you are done, just to use.
Okay, electron microscope. Yeah, that's indeed. I mean, that's as the edge of optics to me, at least. But that's I've heard of people doing that eventually for the cheap. It's tough, I guess. You need to have at least vacuum proven cubes. And others, I've seen some more hands.
Optical tweezers on a microscope.
Yeah, I hear already two aspects. Like confocal, that's already one thing. Tweezers, yeah, that's why I've started doing optics actually. Tweezers, that's actually a pretty cool thing. Yeah, we should have tweezers. Cool. Others?
Light sheet microscopy.
Perfect. One is right here on the table. How come you know? Yeah. Yeah, and I think ideally, I mean, electronics, you have these kits where you then start with like first the blinking, and then I think it's really relatively easy to get things going because it's also very well encapsulated. You just plug things together. With optics, there's no defined standard, so there's not like a plug that you can put together. In optics, if you buy them from Thorlabs, that's one of the big companies. They're not really standardized so that you can put them on an axis, even though optics is mostly you have an optical axis and you chain different like elements together. So this step from like a diagram to something that is actually useful is pretty difficult. Anyway, that's something we want to change. And the way we do it, so as I said, everything is open source. You can go online. There's something here. Is that normal? So somebody was trying. Anyway, the cube is basically just something that holds something. So what you see here, for example, this is a Raspberry Pi Zero that we use for hologram reconstruction for schools. And so this is held by an element that is then fitting inside the cube. You can close it, and the cube is then, in that case, put on the grid. And the grid is then holding cubes in all directions. So you can put them here, you can also extend it in a third dimension. And that's the kind of the idea. And then to make it easier for people to start, there are these kits together with open source documentation. There are, for example, focusing, there's a Galvo scanner, and then ultimately you can not only use that for education, but also eventually for something a bit more sophisticated, like a confocal microscope eventually. And for this, we have this frame. Does it work?
Yeah, I'm
Okay.
going to show very closer to show.
Sure. And so this is the library. I think this photograph I rendered when I was here 2 years ago. I think now we have plenty of more cubes. And what I'm trying to show a bit is like the story behind it, because it's it's out for, I think, how many years? 7 years now, kind of. And it all started with this idea that somebody was approaching us to say, hey, I need a little microscope where which can be used for observing macrophages in an incubator. So macrophages is kind of part of our immune system. And then we built this little thing here. It was basically a Raspberry Pi camera with a retro mounted lens, so that you have. But then they wanted to have fluorescence, they wanted to have autofocusing, and then it kind of grew. And just for today, I've put together some more images. So if you're getting bored, please let me know. It's kind of a family trip with from the cubes here. So this is somehow how it started. So this was already a little bit modular. So you could have like a lens, you could have an ocular, you could have like an adaptive illumination. It was very fragile. Like, I think that was the very I made with 3D printing. Then it got a bit better, but the modularity was lost. And then I was like, okay, we have to be modular somehow. And there were some cool papers. I think the first one I saw was called Cambits, so maybe it was even from Stanford, I'm not sure, where they put together like a camera and something to focus the camera or something. It was also modular. I liked it a lot, and it was probably the inspiration for this year. And here it was all magnetic. So you could, like the base plate was could attach them, was pretty fragile. I think building like an interferometer would not be possible. But then we went over, and oops, that was already the first version here, where you had, you don't see that actually here. So there are magnetic balls inside a base plate, and then just very simple screws, and then you could put them together. It's a very satisfying feeling if you have this click. And so since everything open source all the time, I thought it's a video. Okay, it's not. So you see stripes here. People actually took this idea and developed, like they branched out and developed their own system for quantum physics, to which I'm coming in a bit. We continued. There was the next version number 2, maybe, I don't know, which was also a bit more compatible with Thorlabs components. That was the first device that we put into an incubator, where we merged the Open Flexure, which is also a very cool open source tool, with our stuff. So we made it kind of compatible, because that's also nice. If you're open source, you can just mix and match everything you want, kind of. I think there were more components. I think that was also almost the time where we kind of started writing the manuscript. Then COVID hit, the manuscript came out, everybody was at home and was printing cubes. I think that's mostly also the reason why it became somewhat a big known thing, because everybody was just doing that in the optics community. And so these are the different developments. So we started with, like, I don't know whether it's version 1 or 0, but you see these holes for rods from Thorlabs, so that you can mount the different cage elements. And then that was a bit bulky. Then we reduced the size a little bit, and then we went over to injection molding, actually, because we had some projects going on to serve people with optical equipment during COVID, so that they can do teaching. And then there were, from here to there, somebody helped us. Still the design you have here. Now we have a version number 4, which is slightly different. So we have just minor improvements. For example, you have some grooves, so that you can, because like what's the biggest problem still is, like, if you have this solid here, can measure the speed of light, or like the nanometer precision of, like, can see that here. Like, who knows how a microsinterferometer works? Roughly, yeah, 1. Right?
Yeah, the markers should be at the board here.
Oh, maybe it's. So then, can I put this way?
Pretty sure, yeah.
Okay, and I hope your team won't organize improves these. So the way microsinterferometer works is, for me at least, quite simple. So who knows what's a laser? 1, 2, 3. Okay. So who knows what light is? It's basically just an electromagnetic wave in a certain frequency spectrum. So let's assume we have something, we call it laser, with light amplification by simulated emission of radiation, and this is sending out light. So light is typically, since it's a wave, basically drawn as a sine wave. This perfectly solves the wave equation. But what if we the beam cuts? So along this direction, it will just propagate. So what's happening, like if you look in time, it will go up and down, basically. So if we have something in the way, like let's say a mirror with 100% reflectivity, is like, it will just, oh, my skills are like this. Okay, so it will just be reflected. So at 100% exists. So you see that on the table. Then portion of it goes here, which is like 50%, and 50% goes down that way. Once I put yet another mirror here, which then has 100%, and another one that has 100% here, the beam, or like the stuff, is basically going backwards. So same as here. So what's happening afterwards is like same what happens until here. 50% goes, 50% goes there. So let's assume this is wave number 1, and this is wave number 2. Then wave number 2 will go here, and surprisingly, wave number 2 and 1, they will both be here. So what happens mathematically or physically, I mean, it's the same thing in the end, they will interfere. So since we have amplitudes, they can be positive and negative. screening what's happening here. So this is our wave 1, and this is our wave 2. So 1 and 2. And as I said, okay, so they interfere by means of like every point in time is like summation of the 2 different waves. You have a resulting thing, and you basically just go na. So you have, in that case, they are in phase here, meaning like they are coming in the same time state, so to say, at a certain time. Then they add up. So that's like you have constructive interference. But once you move one of these here, I'll just do that here on the screen, by half a wavelength. So the wavelength is basically determined like the color. So in that case, it's 650 nanometers. And let's assume now it's antiphase. So for every point here, it's cancelled, like 1 plus minus 1 is 0. Then the resulting thing here is exactly 0. So then you have constructive and destructive interference. And this is happening by basically detuning this mirror here, so that when you shift it backwards, then of course the point at which it is reflecting back is a bit delayed. So you kind of prolong this distance here, and then the wave being the screen here is basically shifted. And why did I tell you that? Well, the distances here, which I mentioned here, like the period between 2 cycles here, like one cycle, there's 650 nanometers. So that means like when you move this wave by 650 by 2, then you already have black. So it's canceling each other out. So, and since we have force and back, this is actually 650 by 4. So you can measure the distance shift of black to white by 120-ish nanometer. So when you move this mirror here by 120 nanometer, you already see that there's something changing from black to white. So that means in turn, 120 nanometer, that's actually quite, that's very, very little. So your hair is like, I think in the range of 100 microns. That's like 5 orders of magnitudes more. That's 3, sorry. So then that means your optical system has to be very stable. And typically, if you, so this is still possible with 3D printing. So this is what you can see later. So, and that's why we also have decided to have these grooves, because when you have the laser that is actually able to bend, like, that's not very nice. And that's because the mechanical design of this whole thing, if you have a look here, it's not ideal. So there's no way of putting that straight in. It's also mechanically like very madly over-defined. So that's something we can discuss later, how to improve that. Because what you have in the end, you see that you have 8 holes and 8 pins, and they kind of interact with each other to make a stable fit. And I think you probably know from Lego, I mean, Lego is an exception, but that's not very smart, because mechanically over-defined systems are typically very unstable, which is the case here. It's also very hard to print because the tolerances are adding up. So either you're too big or too small. And with the injection molding, we don't have the problem because it's just done once and then done forever. But we fear the day when people, like when it's a humid day for production, then the material is kind of expanding because it's hydrophil. And then it's expanding so that the parts are bigger, the holes are hence smaller, and it's the fitting is very tight. So there are better cubes and worse. Right, so these grooves, and then in turn should resolve this problem so that you have like some male fitting that fits into the groove, like a V groove, and then you don't have this wobbling anymore, and then everything is a bit more stable. So these are some improvements. We've bought new molds. It's crazily expensive, but it's producing now day and night for like, I think now we're reaching 50,000 cubes now, and that's almost coming back to the quantum bit, because I said there are people, I think I'm skipping that, or maybe no, I'm coming to that in a second. Yeah. some other designs, what we have tried in between. So maybe the Cephala microscopes from Manu recently. So it's
the squid.
good. Yeah, exactly. So we have tried similar things, but rather on an even more frugal aspect. So that's really becoming very cheap. And for some reason, we kind of put away the cubes. And so we built these microscopes that were fully 3D printed, but having the same idea of having a stage and then a microscope, still somewhat modular. And so just to get to know like maybe some source of we literally bought like €100 XY stages, put them in a CNC machine, like carved out the parts that were not nice for us because we wanted to scan these multi-well plates, and then had a very cheap microscope, which unfortunately we weren't really happy with. So we went back to the cubes, and now this is what we have. We call it the frame, stands for Fast Rigid Automated Microscope Engine, just funky name. And the core idea is that you learn with the segments, and so then once you're done, like for example building a confocal microscope or maybe an optical tweezer, it can be one layer here, and then you sneak it in, and then it's just adapting to the rest. So the frame is literally a frame, it's just holding the optics, and the part on top of it is in the stage, and here are some cubes for illumination. And what's really cool is like somebody sent me some plans, and he was interested in getting to know like when the parasites are biting. And so it turned out that this microscope can actually be flipped. And so what you see here are little chambers with plants, and they grow and you can observe them. So that was a cool thing. Also, there's, I think, where it's not open in the sense that you can print everything yet because it's still in the development phase, but it should be open so that people can tinker around. Right, one thing I forgot to mention. So this is the new cube, and this is the new kind of so you can, like, we always try to have two versions so that you can print everything on your own, but also then having some more precision from injection molding, especially if you go into the thousands of these kits. And so this is a new version of this insert, which is adapting to something that is sitting inside, that is then, for example, printed. And so we kind of thought about, okay, what are the imprecisions in printing? So it can be bigger, smaller, and all these things to this new design. So these kind of, I don't know how you, these pedals, they're kind of flexion mechanisms so that you can compensate a little bit the imprecisions in size. And you can sandwich lenses, for example, in between. And yeah, so all this went into this new design, so that you can also print it. It's tolerant against certain invariances in the dimensions, but also you can mold it so that yeah, can scale it up. So this is cool. What you can use it for, well, education, obviously, there's tons of different documentation. You can look it online. People have used it. That's always very cool. I think I don't have a picture. Oh yeah, maybe here. I think these are the best pictures you get. I mean, I don't use Twitter anymore, but somebody sent this over. I think this is somewhere in Cameroon or something, or maybe Nigeria, I forgot, where they had access to our tools somehow. I'm not sure how they went, but he was teaching in French. So he was teaching how a lens works. Like you see that lentille, which is like the lens you can eat. In French is the lens you can use for imaging. And so they use these tools for teaching, which is, yeah, insane, really cool. Yeah, many people everywhere. I think there were some people here in this room 3 years ago. So that I should maybe take a new one. My backpack is still somewhere. Oh, it's here. Right. So the branching. So some people unfortunately only made, but now there are also some more women involved. They have taken one of our states like years back with this click mechanism of the magnets and base their quantum experiments on top. They are very much specialized into building, well, educational material. And so what this is, it's a PCB where you see the little dots here, and these little dots are basically diamonds. And so these diamonds are crazy fluorescent particles. So what you can focal microscope, you can measure the fluorescence. That's one cool thing. And if you apply a microwave on this little strip here, which is basically an antenna, then you can bring these diamonds, which are very funky NV centers if you dope them. No, dope them, right? So that's one. So that you put away electrons, then you have these nitrogen centers with the vacancy centers, and then what's happening there, without going too much into the details here, is the way the lattice is accepting photons is changing at different frequencies, and so when you well, I'm skipping many things because I think that might be a bit boring. When you change the frequency at which you kind of pump the crystal, you see that the fluorescence will change here. So you see like the different resonances from a crystal. And this is all done for, well, I wouldn't say elementary schools, but somewhat schools. And with a system that is printable, but luckily we can also produce it. So it's nice for our company. And it's fully open source. And so they basically branched out, and then they were seeking for a chance to bring that to the schools. And now we can do that together in an open space, which I personally like a lot. So yeah, the first, because I just skipped. So this is, I mean, fluorescence, you probably know from cells, fluorescence in cells, but yeah, this fluorescence is also visible in solid bodies, like the diamonds. And then when you well, apply these different mechanisms, like for example, magnetic. So in the end, I'm skipping a lot of theory. You have a magnetic field sensor. So it's the fluorescence is depending on magnetism. And I'm always wondering how you can apply that to biology, because I think these diamonds can be very small, and you can also attach them to somehow and then put them into the cell and then use that eventually. And they're pretty bright, will never bleach. And yeah, so what I actually want to show is this one picture, which arrived when I was gone. So this is like the first batch of 10,000 cubes. So, and we have 5 more of those. And now we have to bring them to the people. Right, what else can you do with this? And this is a bit the idea, what we can train maybe or like discuss later, this cubification. So I have an idea. I want to have an inverted, how would I do it? So of course you need to have an illumination. You have to have an objective lens, maybe a folding mirror, and maybe a camera. And maybe something that is moving the Z position of the objective, so in order to focus it. And then you can, well, use, for example, the Raspberry Pi Zero to just take time-lapse images or whatever. And then you have the ability of replacing or using a microscope, which you would probably not have in the other place, because the original idea was from this person, hey, which I can use for observing these macrophages for, say, 2 weeks, and I cannot block my Zeiss microscope because everybody's using that. And then, which I would really like to train a little bit, is like this idea of, okay, what I want to do, like optical tweezers is actually, I think, a pretty cool idea. How would I build it? Because you maybe seen that, like from the previous slide to there, only a few cubes were added. So you have, where's the mouse here? Now you have 2 lasers. They're focusing their beam into the so-called backfocal plane. And then you have this here. It's basically almost the same. So folding mirror, camera, here's yet one more lens, but the same principle is the same. So you can reuse all these components all the time. So that's why it's nice to have a library. You can also go for crazy stuff. So here somebody used like a projector, could hijack that one over there to eventually project a pattern and then get super resolution. Some people have used FLIM, so that's fluorescent lifetime imaging. It's actually another company. They wanted to do that, and they didn't know how to build a microscope, so they just used that. And the core idea is then you learn with the cube, you put these cubes together to form an assembly. Like once you have all these different layers, for example, for just the bright field or the fluorescence, you put that into this so-called frame, which is basically just something that holds the cubes together and the electronics at the stage. And then you start doing your image experiment, hopefully at one point. Right, that's one thing. But other things that I have here on the table is light sheet microscopy. And I don't know, who of you have heard of light sheet microscopy so far? Oh yeah, many. It's mostly the optics fraction is on the left-hand side here. Okay, I see. So the way, I think it's the same problem pretty much in all optics. Like if you take I see probably everybody sharp and focus, no matter whether it's first row, second or third. I think it's nice for like if you're on a party and like you want to capture as many faces as possible, but like if you only are interested in one row of the people here, then it's a bit bad because then you have the information of everybody along the optical axis. It's nothing against you. It's just like the information I want to have access to. And so this thing is called optical sectioning. So you want to have a section optical paths of your volume, especially in biology nowadays. Many people work with like these organoids, and then you have big assemblies of cells, and you only want to slice like a certain piece of it because it's very turbid media. And so the way you could do it is, let's assume this room is dark, and I just illuminate from the side, maybe with a projector, like the first row, and then the second row, and then the third. And so this is literally the idea of light sheet. So you have a sheet that is literally just illuminating space like one row at a time, and then either you move the light sheet or together with the optics, or you move the sample through the static light sheet. And then the idea was, back then when I was here, to do that for plankton, because I think there's this notion that, like, depending how the shape of the plankton is, it will sink faster or slower to the ground and eventually capture more or less CO2 on the way. So it's interesting to know what's the shape of a plankton. This is an animation. But there are other techniques like confocal microscopy, which is laser scanning. It's very expensive. You cannot bring that on a boat, for example, to, get to know the information. As I said, so light sheet microscopy works the way that you don't illuminate the same direction as you were getting the information back. So typically you have, for example, LED, you illuminate either from that side here or from that side. The force are excited, the information goes back to the camera, and then you see everything along the optical path. But in light sheet microscopy, you have the sheet coming from the side, the sample is in a tube, and then you slice it like while moving, for example, the sample through it, and then you capture through this side here. And surprisingly, since this is already very rectangularly, it's very easy to build with cubes. So what you have is a laser. It's shaped so that you have this, well, it's not only a point, but like a sheet. So it's a cylindrical lens again. So it's a rod lens forming this thin sheet. And then you have your sample here. You observe that, and then you translate that to the cubes. And again, I would like to train that, or like at least get an idea how you would do that, from idea to like the UC2 cubification, and then to the setup here. So this is a bit like MRI. This is a zebrafish where they label some neurons, and you move the sample through the sheet, and you see the responses there. And then once you have that, you can have the 3D volume. That's the same we have done last week with some plants. So they had some GFP labeled Arabidopsis. Looks pretty nice. And also 3D printed samples. So a friend of mine, she's working for this company called Nanoscribe. So it's a 2-photon printer. And so these structures, like for example, this like this spiral over there, I think it's like 50 micrometer in diameter. It's a polymer that is UV cured in a way, so it absorbs in glue and it's quite fluorescent. So this is what we have there. Right. This is super nice for stationary samples, but not super nice for like many samples. And the ocean is full of samples. So what we wanted to do was high throughput. And so the way we did it was basically you have a rotating tube, you have flow, and then what's happening is the sample is rotating through the capillary while you capture it. At least that was the idea. I think I had like 2 months, and that's the data we required. So the prototyping aspect of this was quite nice. And so then if you have real samples, I think this is something we acquired when we were in Monterey. It's not, so this is some algae. This is the 3D response here. For the light sheet, it works quite nice, but for the holography part, that didn't really work that well. And that's, well, the holy sheet is kind of, so it didn't really work, but it also was quite fun. Cool. Is there more? It just looks funky. So these are some Nematostella. Yeah. So I don't want to overwhelm you with too much technical stuff. Maybe we can also go into the details, like what I have here, and then discuss a bit more. Some closing remarks. All the optics also need control. And so the way we did it, also they're open source. We have a little board with a fully modular control all kinds of different elements like motors, lasers, galvanometers, stuff. And this is, I think, a good example to show that it's actually working. And what's also nice is, I mean, it's probably not only true for the ESP32 that we use for microcontroller, but also for others. One thing that always annoys me a lot is installation. And nowadays, modern browsers, they can be used for controlling, for example, your webcam. I mean, that's something not now, but typically used for kind of Zoom, not Zoom, but like Teams stuff. And so, but you can also control your USB hardware. So you can connect to your browser without installation anything. You can, for example, manipulate and observe this microscope, which I personally like a lot, because then if you're in a class, you don't want to install apps all the time, because people sometimes don't want that, and then it just works out of the box. Another thing that is then becoming a bit involved, because you have a camera, you have a stage, you have a laser, maybe some image processing, and all of these different elements have to work in a orchestrated manner. So like move the sample, take an image, move the sample, take an image, capture all these things like in storage, and then eventually display that in 3D. And for this, we have also now together with Ethan actually a full operating system, which I think like a month ago would have never believed that it's actually possible, where the control mechanism, the display mechanism, everything is packaged in something that's called the Docker image. For me, it's something like a huge zip file with all the ingredients that we need. You flash that on the SD card, you start it, and it's just working. This is a bit of a magic. And this is something we can also have a look now, because the light sheet is hopefully operatable, we'll see. And where this is eventually coming helpful, like if you not only have a microscope, but maybe also like a pipetting robot and all these things, and you want to put that in a workflow all together. That's something also we work together with some people all in the open, which is, I think, pretty cool. And I think I'm skipping all this here. And finally, this is some people of the team. Actually, the team is now bigger. I should have more people. And together we're kind of trying to democratize microscopy. And I haven't prepared anything more than this here. So we just go over to the microscope. So let's see whether see that. Yeah, it's alive. Cool. So this thing here, let's see, can I no, what is the full screen mode is not here. It doesn't matter. I mean, you see it anyway. So let's see what the camera works. Yeah, looks good. It's dark. You can also come over and we can try to have a look. Okay. And so this here literally is following this idea of having a light sheet. So here, so how everybody can see that. So this magic cable here is a laser. So right now it's off, so don't worry. There's the lasers hold here, the fanning out, and in order to collimate it so that it's parallel light again, you have to place the lens where its focal length is, or like the focal point is here. So then parallel light, this is a cylindrical lens where you have only one surface being bent, the other one not, so it's not symmetrical around the optical axis. The mirror, which is then just transporting the light here, yet another lens that is projecting the light into this little aquarium. So aquarium water actually, because what optics like is flat surfaces. So if you look through something that is bent, then optical quality is typically degrading. I mean, that's why lenses are.
This is a straw.
No, not almost. So this is it's a special material, but good that you ask. So this is it's a tube where the sample's inside, and the refractive index of the material is the same as water. Means in water it becomes fully transparent, and so that means the light is not scattering at all. So that means yeah.
What is that material?
It's Teflon. So FEP stands for fluoride blah 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 bromide. So this is yeah, if you look, so there's a little chamber filled with water, and I see also why there's some light, because there's like a not chewing gum, but like that.
And there's glass windows.
Yeah, exactly. If you look from this side here, you can see okay that it's actually an aquarium. Look, from that side here. Yeah, you could find either.
How do fine adjustments work? Are they needed? Or like the actual like
For the sample motion, there's the state. And for others, I mean, you see that here later. In there, you can move it precisely. You could put away this here. My magic glue. And checking whether the camera is actually working. I don't see light on the detector. All right, this. Sure whether we can actually see stuff. Oh yeah, okay. So you see something there as well. That's good. Okay, now when we insert the sample, so this is this 3D print sample on glass. So it's this little structure. Let's see whether we can see anything. Is there anything on the screen? Was there anything? Not yet. Okay. Many people out there actually. Oh, there are actually people.
Yeah, there's a
Well, we're not alone.
there's 11.
Nice. Cool. Okay, let's hang this down. Okay, there's already something. I'm absolutely not sure whether it works. Live demos are usually never. Okay, so then where's my PlayStation controller? Okay. So precise control is kind of done over this here. So you can move the sample, and this is then moving up and down and to the side. Let's see. I see. Ooh. There's some dust. Dust is always good. Okay, let's see. So now I'm curious whether you can focus it or not.
this is the printed on glass, you said?
Hopefully, yeah. And I see. So let's see. Is there the motor? I'm not sure where the sample actually is. Can I see for a second on that side? Okay, it's way too high. Oh. We've lost where the sample maybe. Well, let's try. So the fluorescence aspect, so I'm turning off this here. Completely off. There's the light sheet. Okay. Well, that's like the stuff I was just saying. Live demos are interesting. Let me see the light sheet actually. Where is it? There's a piece of paper in the way. That's it. I need cotton. In the meantime, I'm curious. What is your background? And so I see some people know microscopy, but what is it? Biology, chemistry, computer science, social science, or what is your background?
Biology, plants.
Plants. Okay, so Arabidopsis is something you have heard
Oh,
before.
yeah.
Nice.
Look at those leaves all day.
Lucky you. Did that help already? Yep, that's better. there something? Ah, there. Okay, we see at least some signal. That's good. Now we can iterate. Not
Oh,
sure what we see.
Are you spinning it?
No, and my brain is a bit. Let's see. So we're right at the border of the motion, I guess. So so what I'm trying to find now is the 3D printed structure, but
Yeah, looks like it's being stuck.
yeah, it's running against the border of the chamber. Also not sure what exactly we're looking at right now. Complete. Anyway, last approach to. Well, if not now, then maybe later. I think also the camera. Anyway, okay. So, but this is the way I think I'll try it out in a second again. To build a light sheet microscope where you have light coming from the side, you illuminate that, you move the sample at X, Y, Z, and then you have a microscope, which is basically a fluorescent microscope capturing that from the side here. On the other table here, you have the micrometer. It's exactly what you see there on the screen. So here it's laser. You have the mirror. One fraction of the light goes here, one fraction of the light goes there. So you turn on the laser, and you actually see two copies of the light. So one is coming from this arm, the other from that arm. And so in theory, now if we put the two waves, so you have to think, okay, this is a wave band, so it's shooting out waves. It's literally oscillating in space. And then they are hitting the screen individually. So either that one or that one. And so when we move them closer to each other, that
would it help to turn off the lights?
Yeah, someone hit the lights.
yeah. Then you see these the
Other way.
Yay. Okay, so you see, it's actually not quite dark and white, and it's quite okay, but it's rings that we see there. And the reason why we see rings is it's actually not a plain wave that is coming out of the system, because I intentionally kind of detune it. So there's a plain wave coming out of this laser, but then there's another lens that is making this wave go kind of divergent, so that kind of have a bigger spot in the end. That means the beam here is divergent, so that means the wave in the end is not parallel, but rather it's a sphere. So it's going on spheres or parabolas or something.
It's like alternating between waves and.
Yeah, exactly.
That was interesting.
Yeah, so yeah. So when you have a wave that's spherical and you do the same equation by means of wave 1 plus wave 2, and it's yet another sphere. What's happening is then you have sphere plus a sphere, and since they are in 3D, it's actually cut. It's more like a ball with a ball, half ball, or half sphere. And then wherever you have a 1, you add 1 plus 1. Wherever you have a, let's say it's -1, because it's a sinusoidal still, it's 1 plus minus 1, which is 0. So that means wherever you have like the dark spots, it's interesting. It's vibrating quite a lot, so that's why you see this.
If you talk, would it pick up the vibrations of your voice?
Yeah. So also, it's like when you're like touching the table, that's like every motion here. So if you have like what's called solder iron. Do anybody see solder iron here? Because if you heat up one of the elements here, that means it's expanding. Whenever you see 100 nanometer or 120 nanometer in variation in one of the arms, that means that you go from black to white. That is the so when you, I mean, if you have very hot hands and you have that like this, that very good. So at home, like for the students, there's a little heat element here, and then it's just expanding a bit, and then you see that it's quite fast. And so I mean, where is this useful? I think there are ways, for example, measure the distance from here to the moon. So there's a mirror on the moon, and then you measure the distance by means of the runtime when the light goes up and down. You see that then by the when you compare the two copies of the light. Actually, so
There's what isn't this also used for the gravitational waves project?
Exactly.
Because like the waves, I don't understand too much. They will affect these two arms differently, and with the length of it, you can have more precision and resolution in those set of gravitational waves.
Exactly. Yeah, I think this what's the experiment called? There's one in the US, one in Europe, and so that you measure the same elongation at different times, different locations. It's literally exactly this here. So they have a laser, a bit more and then this arm is like a millimeter or something in a tube, and then so the coherence of the laser, so that means of like how much can you move this thing so that you still see interference, the ability to sense black and white stripes in a way. This is probably a little bit different than what this here. But another thing where it's used also where you may not guess it is when you go to the like the eye doctor of this funky word. So there's a technique that he uses exactly this here, where they literally point this device to your eye, and I mean right now we have plane surface with the same plane surface, and then you exactly have this grid pattern, but you can we have any surface that is reflecting light and compare that with a known surface, for example, a plane, then you see just a different interference pattern. So what you do is always wave 1 plus wave 2. And if you know wave 1, you can basically back propagate wave 2. And so in your eyes, they do that. So you're reflecting one portion of the light. And then you have a reference wave. In that case, so it's wave 1, for example. And then they look into the depths of the cone so that they can project the 3D structure of the cone and see whether you have a cataract or something like that. It's called OCT, it's optical coherence tomography. Pretty cool. And here, to be very precise, actually, so to really see the 3D structures of your cones, only one wavelength, but you have many of these wavelengths, so you measure in red, green, and blue. And then for every color, you have a different wave interference pattern, and then you get better 3D sectioning than one. Yeah, it's a pretty cool technique. So, OCT. That's how it's only set for October, but optical coherence tomography. Yeah, and also there was somebody indeed building this just to emphasize the cubic. So I think what I would like to do now is I've seen at least some people here in the group who had some ideas with optics. So who would be keen on designing a system based on what you need? So let's form like 5 groups or so. So we had, let's collect ideas. So we had optical tweeters.
There's this optical component with some people on the left and on line as well. We're trying to design a CO2 sensor with the wave modulation spectroscopy.
Okay.
So I think we could do it with your purification process.
That's very good. So we have spectroscopy with the wave modulation. I'm not quite sure how this setup looks like, but
I can show you later. But I think we could do it.
Yeah, I think perfect. So I think everybody chooses, or like maybe in a group of 2-3 people. So then we have 5 groups. Wouldn't say a random setup, but like something you are interested in. For example, a confocal microscope. Look up the diagram, like any manuscript, like even the
light
paper
diagram or optics diagram, they'll show you the light paths and where mirrors and things need to be, right?
Yeah, exactly. So look up the diagram, then we try to convert that into like a cubified system so that you know, okay, this has to go there and then we can maybe discuss like what's missing and then how you will do that. But in the end, it's not so difficult. Okay, so then go out and do stuff. And in the meantime, I try to align stuff here. Give us a power. One cable lost connection. So I have to restart. Like, this is-
I think there's also a Docker command you can run to restart a container you already have. That might be useful.
Yes. So would it when I restart?
Actually, so what we do in Plaintiff OS is I have a browser app for looking at and managing the Docker containers. You can look at the logs, you can restart containers.
Interesting, because this I implemented at least I started preparing that yesterday. So so the system settings so that you at least can restart stuff.
Okay.
But I didn't think about the Docker. That's actually very interesting. So that you restart the Docker compose, or you have something.
There's a Docker command you can run to restart any container with the compose app
within the Docker
Docker,
container,
yeah.
from the running container, that you have trigger signals.
I mean, you would run a command, a Docker restart container name.
Okay.
Yeah.
That would be very helpful. And would it then also remount the hardware? Because I figured like when you disconnect the hardware, it won't recognize it again.
We would have to test that out. It depends on how the hardware gets
Okay.
used, like the mount or the kernel or whatever. Yeah.
That would be actually very helpful.
Basically, yeah, you should not need to do Docker compose commands.
Okay. Maybe run again. Oh, this is the wrong. 5 was the one for the LAN, right?
5 is the one for Ethernet. Although 4 should also work if it's making a Wi-Fi hotspot.
Pretty good name.
Because it has to keep it here. So
What happened?
no, this is the 12 volt to 5 volt supply, and you have to explicitly push the button, otherwise they won't be. And I restarted it too.
I see. So this is like a just empty space thing.
So there the filter goes.
Oh, okay, I see.
Let's wait until this back. So so you want to build a person microscope? Yes. Nice. That's a very good one. If the speaker just, I mean, it's already pretty difficult. So you see, I mean, here you can nicely draw boxes around it and then you're done.
Yeah. That's exactly.
Oh,
Is that the 50%?
almost. It's to me, it's a bit like a light bulb, and so it's like certain needs and not like reflector.
Oh, see a block.
That's all of them.
Yeah, so there's a difference between reflection and absorption. Some of the divergence. The diagrams, they have a step lens where they reflect everything above. Sorry, below and produce a whole mirror, so they reflect everything below the wavelength limits, then currently everything above. So
And can you change that within a single mirror, or did this swap out mirrors to get different switches?
So there are mirrors that have multi-band, turn on and off at certain spectrum ranges. For example, here it's kind of a greenish laser, so it would reflect the green, but it means that it's could be of course have the slope shift to the red. And that's so that's why it's kind of a light bulb, because let's see certain colors, but it's not. In the rotation filter. Nice. So usually, I mean, back then in the days, you have lasers, so you have white light. Then you want to filter out, for example, on the green part. So that's why it's absorbing everything above the green.
Yeah,
Theoretically, no, but in practice, usually the lasers they have some weird sideband, so that's why they need to be cheap. So they don't have any. I mean, laser has like a laser, they have like spectra. That's why you want to get down. And what's more important though is the initiative. Okay. So that you, because the like words are not they are only in the basic function form. And so this is talking everything that's not supposed to be coming from the website. Is everything about the and I think that was pretty complicated.
because if you have a mirror like this, you have to like it's on
Yes.
Single laser.
So there's the database called
So where you can, but really,
they only recommend you which
targeting specific absorption. This is like near red. And like modulating the current.
So they are for like you have like multiple layers.
You get an absorbing like signal from the photodiode. And then you can deconstruct this signal.
If you go to our website, which is open use,
Yeah,
it's very much the rest of my service. It's already where,
So
when you go to
Like,
probably tutorials,
AM radio and
patient activity,
well, at least I'm just where I slide station at least.
so
make sure
that's good.
Well, what is that back order? Like,
Yeah.
only by.
Yeah, one of them.
So. Yeah, thanks. I'm not sure how they actually.
So what are you trying?
Like I just right now, brought like yeah.
We're looking at, that's.
The whole school about it, so you can actually monitor the lasers, right? Just bringing this. And
So
that's
like
where you
full
can actually
illumination
measure
kind of
the
thing?
absorption.
Yeah.
And it's like sensitive or
I'm
looks
so
like
sorry, complicated.
like
It's what I'm
baseline.
trying to make sure.
And that's
Yeah.
like completely dark. And you put
Yeah,
it
that's
in the
good.
light.
Uh-huh.
But the way this works.
Or you probably would.
Especially. Insensitive.
Well, like everything that like realize somewhat
Any
realize.
implanting this.
So that's
So you
why
go
it's
from
what
like,
you want to actually.
It's that way.
It's easy.
Measure.
So
Yeah.
getting
Yeah, then you put.
section.
Or, yeah.
And so in questions, it's.
Yeah, and then
just like,
overlay.
for example, so that.
So like it does whatever.
Yeah,
Or five.
It was so what you want to do.
It's actually imaged in gray.
So you have getting sound.
So you can actually cheat also like alter whatever. you want. And you can like, you could like make that same photo, just completely different font.
And then you have an object.
Like you're allowed, like,
then capturing.
Dappy is traditionally stained in blue.
On the.
Yeah.
So like, it's not actually blue because at that small scale,
Have
you
a.
can like alter it, whatever.
Like a schedule light.
Yeah.
And the back is weird from your.
Yeah.
Camera.
Yeah, it's actually just, it's dark versus white.
Yeah.
But then you just get-
So it is.
Yeah. You just like, pick what you want.
What's happening there? There's a scheduled light.
And then there's multiple different color processes.
They are all still in phase, so that means.
That was your project along?
Like a certain origin,
It's fun.
and then it goes through the lens, and then they interfere on, in that case, the perfect plane location on this center. And then you can kind of very reconstruct which unfortunately never really works because yours that's okay, it's not perfect.
And we have a model.
Get frame back on the sensor.
Yeah.
This is. So you have a certain.
Okay, so
way
it's
of using your.
I got like,
Okay. Do you do the side?
well,
it's
normal
sliding things.
most
So.
Louis, right? Am I good for you? What is the quarter?
Then it's only.
Are you doing the same thing as?
Cool new photos recently.
Well, I think then maybe something else would be. I think the rest of Mexico is a bit more. So.
Yeah, we're only set.
I think you really know where to take it.
Got a few microscopes, so you have to do the.
So, your face,
There's laser,
So oral biology, like oral is really it's very hard to do it. So it's a colonial. So like the whole, like let's say like the close up my finger. My whole finger thing is a line. With each of these spots is an individual. Like, and they're all connected through tissues on the outside of the skeleton for years.
what happens, like.
But each of these is alive. The one where you would take 20 other people's fingers, they create one. So like, they're all clone to each other.
Which.
Then they age to reproduce, so they'll really like go like this. But they also sexually reproduce. But it's releasing gametes out into the water and then another full meets up and they spawn to make little zygotes and swim around in the water and then land.
I mean, it's probably,
Yeah, and they'll finally image
lens, like from CT forward into like focus spot, like
healthy corals like dark.
already set the Frugal.
It's all, those dark ones really concentrated with
holding true, like
one
one
little
source.
symbiote.
But then
Like that's individual
it's the
symbiote.
focal length.
Whereas in the bleak one,
To infinity plus. So this is kind of homogeneous, and this is the idea of level station. So.
like, yeah,
Why
white.
makes sense here are like some of like reader lenses like where you say you have
And then that's the follow-up.
kind of point source.
So like when you think, you see that something like veins just like rock and everything, those get a little thin layer of tissue surrounding it, and they have these little problems.
And then
Well, we're making progress, but yes, we got, I think we literally have 3.5 weeks. Like, one, yeah, we just had, yeah, one, oh, maybe 4.
So this is why.
Oh, yeah, well, yeah, well, yeah, we got presentation tomorrow, on Wednesday, that's gone, 1, 2, 3. I think finals is right around.
Yeah, here's the final thing. There's like a transillumination. Well, yeah, this will be. I also have like no experience, trying to read.
We're working on this afterwards,
So this is like.
we'll see. But-
Commander or. Yeah.
There's this.
Oh, well, like this is what I, like this is what I'm working on, it's like. This is- Oh, okay, like these are some things that are really one, so like, blue skies, and then we just have like signs of recovery.
Same idea.
So these monitors. are the same one. Oh, we talked about the disease briefly.
But then these just.
This is.
Back here. Oh,
Well, I can't believe how small
But
it
there's
is.
there, which then shipping design such that it's one homogeneous example.
Oh, I thought the problem was saying like the only area I'm like a very small, like 2 mile area.
Make this. Yeah, it's well, that's the video.
Oh, like,
Yeah. Hey, so this is what I was talking about.
Because of
And then
warming weather.
by monitoring the
They're going to-
current, actually, of your sending that diode laser.
Yeah.
So keeping a high frequency and passing it through the that way, your signal is sensitive to like concentration.
Yeah.
And all you need really is lasers have the. And it's super fun to try.
That's actually pretty good. So, but some things I'm always been scared of, like, yeah, it sounds amazing.
Yeah, it's pretty fast. It's like, I wanna say. So I like,
And what are
I used to look it up, I wanna say like negative.
Science, cracking his field, building real cool trackers.
I think they're kind of the same.
All the parts are the same.
I know it's like done somewhat, so like.
Yeah, lifting more, lifting the gather unit or putting down.
Oh.
When I showed was,
No, but it was very.
Somebody has to. Like, they got little trackers. You're literally never gonna do trackers. But there you go. They do have a lot, yeah. Like that's way larger. Yeah, I don't know how much you get to make a lot of
Gas concentration of blood. Like on.
Yeah, and then 63 of those.
Cool. No, the companies so you, selling that as well?
But yeah. I mean, it's. It's a cool thing. It's
So like we track like the whole swirl.
And the actual
Oh, of course, any cancer.
That.
Yeah,
Probably.
Watson.
You have to find out like what's it and then like then make it an ingredients. And so really that does. Like part of. But yeah, you have to have some ways of increasing what it is.
Yeah, really.
So you're gonna go like, if I were to, how do you? With the light, get to the ice.
Yeah, this rotation is not there. So it's not the X, Y, Z, the thing. So, yeah. So you do the rotation level, I think, in the water. Control, I have.
What do you need? Just give me those. I'll read that instead.
By the way, you try to do that's there.
No, I prefer to go straight on. Perfectly straight on.
That's related. I guess so, yeah. I think what you just need is like a very well. Right, it's pretty much like.
Not societal. You're just jealous. So I still have probably.
I've been thinking about.
Like I haven't finished how we can scan around. I do want to do it. But.
So instead of just having like but you're saying you just have to adjust it's not this way, it's like that's what we look for. Yeah. That's where I was concerned. You want to go get I don't. I've been like the companies where going to get her bridal gown, and everyone's like drinking champagne, comments and you know what makes your hips look big. Angular bio. What's that? But it's because I wanted to experience everything. And I wanted to be parallel here for better rather than define this like I know this one. Still like years. Yeah. Yeah. I was comfortable with the always, yeah. I mean, if you have a there's some educational for users. Absolutely, yeah. Yeah.
There's two different stations.
This is all rad. Thank you so much.
Absolutely, my pleasure. It was nice. Yeah. So it's a bit of a pity that this doesn't work, but
That kind of live demo is all.
yeah, it should.
It's because I mean, when I see a lot of this stuff, I think of how a lot of fancy microscopes have like all that kind of thing. Everything's very isolated from dust.
Yeah.
Does that end up exactly overhyped?
Well, no, it's not overhyped. I think you'll see that. But I mean, in a way, it's also a good thing because you can actually open things.
Yeah,
Like
you can open it.
Yeah.
It's not.
And if you have an iPhone, if you open it the first time, you can actually like dust, so you see like certain it's really hard to see. Yeah, here you could prove the whole thing. You know,
Yeah, and it's just
it would survive for sure. So it's
nice.
we have to set it in a standard.
Yes, that sounds good for me. Well, thank you so much.
Yeah, nice. Thanks. Yeah.
Thank you, it was nice.
Situation, I'm thinking of,
So,
Okay. Just a heads up, yeah, yeah. Yeah, okay. And then, so there's a sense of where. Yeah. Yeah. Okay, yeah. Yeah.
so
Yeah, you basically you're gonna go to you're basically committed to a team. We could like wait, no, we could very well we could very well put it on for this okay. I would say in terms of emphasis, like the presentation, like 70-80% focusing on the problem, and then 20-30% on solution. Like that, the solution it will come in the form of a red heart and all the solution options. But in terms of pinpointing which one, like don't worry about that just yet. But you can think about it. We want to see the options rather than like the narrowed down. Yeah, and all the options and possibilities, because like in each column, you basically list multiple options. Right? These are like design or yeah, there's multiple options. Yeah. Yeah, I think. Yeah, I mean, when I don't know if you saw the video when he was doing it on the board, but he was like, "Oh, these would be design parameters if we assume this type of solution. And these would be design parameters if like you can have them all. It's but maybe you can highlight or color code based off of like what kind of solution category there will be overlap. It's going to be messy, but it's different. About that's like the whole different something. Like something when you get
interesting. The camera is barreling out if there's too much light. The camera is stopping when there's too much light.
Oh, fascinating. I've never heard of that kind of video.
I mean, maybe it's because I don't think it's current consumption, is it? Or maybe the laser uses too much current for the rest.
Yeah. Are you powering the laser from the Raspberry Pi?
No.
Okay, that's good.
But it's I don't understand that. Because the camera stops working when I turn on the laser. So I know I don't have any way.
Turn on the laser first and then start the camera.
Yeah.
I'm curious if the camera immediately shuts down.
Yeah.
Or
I mean, there's a mechanism to eventually reconnect it, which it looks like it's also failing. So,
I think you should be able to do like, instead of the long text name, you should be able to use the name of the container.
maybe, but the container's name is also quite long, isn't it?
Oh, maybe it is. We can, if you do Docker PS, that should show. Yeah, I don't
share.
recommend doing it this way.
But how would I? Yeah, okay, I have to.
That sounds like data analysis. In addition to that,
I mean, having a restart option, that would be very nice.
physical aspects to it.
Yeah, the restart option is kind of Docker, although